friction. Now, if you watched my last video about the hay bale, we learned a little bit about friction and about how it's a force that opposes motion and it's necessary in certain aspects to create constant motion. That's motion that's moving with a constant velocity. Friction exists pretty much everywhere in the world. Um, a lot of times in physics, we like to live in a nice little isolated box where nothing real happens. But in reality, right, friction happens everywhere, okay? Um, and so we need a way to deal with this. And it's really not that bad to deal with. It's just another force to add to our free body diagrams. Now, there are two types of friction. There's kinetic friction and there's static friction. Kinetic friction means moving friction. So that's the type of friction when something is moving already. There's a different type of friction versus if something is static, that means it's not moving, right? If it's not moving, there's a certain amount of friction uh, apparent between that object and the ground. Now, remember, friction depends on how much contact there is between the ground, which means it only makes sense that friction depends on the normal force. So this is your trusty dusty friction formula that you will use over and over and over again, okay? It's made up of two different things. This mu, this little u with a front tail, that is called the coefficient of friction, okay? That completely depends on the materials involved, and what type of objects you're working with. That is a constant that will either be given to you or you might have to solve for it. The other thing is the normal force, and this normal force is exactly how we calculated from our last part, right? Calculated from the sum of the forces in the y direction. Okay, it's different for every question. You always have to calculate it in the y direction and then use it to create the friction in the x direction. Okay, now remember, and I can guarantee you some of you will forget this, friction always acts in the opposite direction of motion. Always, always, always. There's no point in life when friction will actually make an object move forward rather than slow it down. Okay? So it's always acting in the opposite direction of motion. So let's talk a little bit more about this coefficient of friction thing. We said there's two different types. There's this kinetic friction and static friction. And we say that there's a mu k and a mu s. Now, there's a difference because if you think about it, is it easier to start an object moving from rest or keep an object moving? I want you to think about that, and we're going to start class with that tomorrow on Thursday. Is it easier to start an object moving from rest or to keep an object moving that is already going? Okay. Now, we're going to skip that because that's just kind of the answer. But in general, what we see is that the static friction is bigger than the kinetic friction. So some examples of this value is if you've got wood on wood, it's got a static friction of 0.4 and a kinetic friction of about 0.2. Ice is about 0.1 static friction and 0.03 kinetic friction. Where if you think about it, if you have a block of ice sitting on ice, it's kind of hard to get it moving, but once it's sliding and you're skating on ice, there's hardly any friction at all. So this value is very, very slow, very, very low, I mean. Rubber on dry and wet concrete. This is interesting for those of you who are starting to get your license. When you've got a car tire and it's dry outside, you've got a coefficient of friction of 0.8. But if it's wet outside, if it's raining, your coefficient of friction drops by almost half, down to 0.5, right? So you're losing about half as much friction that's actually keeping you on the road. So just something to keep in mind when you're starting to learn how to drive. Now, these numbers in this table are just meant to be a guide. They are not exact values. You are not going to be referring to this table over and over again. This is just an example right now to give you a general idea of what values are. The coefficient of frictions will generally be given to you in the problem, okay? Or the problem will specifically state solve for the coefficient of friction, okay? So my favorite way of thinking about friction is essentially as a percentage of the normal force, okay? That's how I like to think of it. This normal force is this contact force, and the coefficient of friction will always be a decimal, which means you're always going to be having some type of friction force that is some portion of your normal force holding your object back. The coefficient of friction will rarely be over 1. It might be in very sticky situations, but it's going to be very rare that it's that high. It's not a percentage. I do not want to tell you that it is a percentage because it's not. But if you think about it, you're taking your normal force and you're multiplying by a decimal, which means in reality, you could think of rubber on wet concrete as 50% of your normal force. That's the amount of friction that's holding you back. Again, that is not the mathematical definition of these coefficient of frictions, but that's just one way to think about how much friction and how your coefficient of friction relates to that. So let's try some of these in an example. So I think I can outsmart all my students by placing my mystery box on a rough surface so it's hard to steal. Whenever you hear rough surface, that rough surface means that there is friction present. Okay, a slippery surface means it's frictionless. A rough surface means there's friction. Now it gives us two values, a static friction coefficient and a kinetic friction coefficient. The static friction is higher than the kinetic friction. So we want to figure out the amount of force needed to start the box moving. Now, a very important thing about these types of questions is if you are starting the box moving, that means it's initially at rest. And if it's at rest, you are using static friction, which means your coefficient of static friction in this case is 0.4. If we want it to start moving, the condition that we are going to look at is right the second that it overcomes this acceleration, this friction. So we are going to look at the condition when our acceleration is equal to 0, because that is going to give us when it's still not moving. Okay? Anything more than that, if we were to look at even an acceleration of 0.000001, okay, that is essentially 0. So anything more than this value that we find with an acceleration of 0 is going to give us a box that's going to move. Okay, this is the minimum force needed in order to get this thing moving. Okay, this acceleration equal to 0. So in order to get this thing moving, this question, we need to draw a free body diagram. So there's our box. We've got a force of gravity going down like this. We've got our normal force going up like that. Now we're going to assume we're pulling this completely perfectly horizontal like this. So there's our applied force pushing to the right. Our motion is going to be to the right because that's the direction of the applied force, which means the friction is in the opposite direction, opposing the motion. So the sum of the forces in the x direction is just going to be our applied force minus our friction force, FF. That's totally cool. And in the y direction, we're going to get our normal force fighting against our force of gravity. Now, this y direction is really nice. It's not moving vertically, we know that, which means in this case, our normal force is just the force of gravity, which is mg, which is just 10 times 9.81, which means we have a normal force of 98.1 newtons. That's good to know. Whenever you have friction, it's kind of important that you should know what your normal force is. Because we can now go ahead, and I'll do this in blue, we can take this and look at it in the x direction. Okay, not in x, in the x direction. Okay, what we have is the applied force fighting against the force of friction, and all of that is equal to 0. And that's because of this nice little note right beside it that our acceleration is essentially 0. So in this case, our applied force is just equal to the force of friction. Well, the force of friction we learned is mu static because it's not moving times our normal force, which, good thing we know all of those values already. We have a coefficient of friction of 0.4 and we have a normal force of 98.1. So we plug that into our calculator, and that means that we have an applied force equal to 39.2 newtons to start motion. Anything less than 39.2 newtons, and it's not going to move. Anything above 39.2 newtons, this thing is going to start to accelerate. If you pull at 39.3 newtons, well, sure enough, it will start to move, but it's going to move very, very slowly. If you pull with 100 newtons, this thing's going to move much, much quicker. Okay? So, what happens if a sneaky student tries to pull the box horizontally with 45 newtons? Is it going to move? That's our first question, right? And since 45 newtons is greater than the 39.2 threshold that we just found in part A, then yes, the box will move, right? Unfortunately, for me, this student will succeed in stealing the mystery box, which means we don't really care about static friction anymore. All we care about is now there's kinetic friction, right? Now there's kinetic friction. So our coefficient of friction decreases and is now 0.3, like it told us in the question. So all the stuff here is kind of exactly the same. So I'm just going to take this and I'm going to copy and paste what I did up here. We have my free body diagram. This was just so beautiful. I want to replicate it like that. And we've got our two sum of the force equations in the x and the y direction. Since nothing here is changing, nothing's pulling horizontally or vertically or anything like that, we're going to get the same normal force in the y direction. But the biggest change is that the sum of the forces in the x direction will equal mass times acceleration because we are pulling much, much harder in part B than we are in part A. So, using that idea, we can take this same sum of the force equation, Fa minus the force of friction, and make it equal to mass times acceleration. So we want to know what this acceleration is. So our acceleration, divide out the mass. We've got the applied force, which is 45. We are subtracting the force of friction, and we are dividing that all by the mass. Now, be very, very careful here. This force of friction is our kinetic friction times the normal force, because this box is already moving, okay? This is not 39.2 newtons like we found up top, okay? It is a different amount of friction because this box is already moving. So just be careful about that. So if we take our values here, we've got 45 minus 0.3 times 98.1. That's our force of friction right here, okay? And we're all going to divide that by 10, which is the mass of the box. We are going to get a nice acceleration of 1.56 meters per second squared. Not a huge acceleration because we're not really increasing much past our 39.2 Newton threshold, but it is still quite a significant acceleration. Now, part C for this question is going to be very similar, but now this student is going to pull this box at an angle of 25 degrees with the horizontal. Same amount of force, but now they're pulling it at an angle. So we're going to follow the very, very similar steps to this, except we are going to pull at an angle. So first step, free body diagram. Always, always, always a free body diagram. Here we have our force of gravity going down. That hasn't changed. Our normal force, that's going up. That hasn't changed. We have our force of friction opposing this motion. That hasn't changed, but what has changed is now this poor soul is pulling with this applied force of 45 newtons at an angle, which means we need to break it up into an FAX component and an FAY component, because this person is decreasing the amount of friction between the box and the ground. So we can kind of jump here right away. We're really good at vectors right now. We're just really feeling vectors. So we've got a 25-degree triangle right here. We know they're pulling with 45 newtons. We've got our FAX over here, which is going to be equal to 45 times the cos of 25. So our FAX value is going to be a good old whopping 40.8 newtons. And if we do exactly the same trig, our FAY is going to be 45 times the sine of 25, which is going to be, our FAY is going to equal 19 newtons. Okay, that's fantastic, absolutely fantastic. There are our two vector components. So up next, let's go to the sum of the forces. So let's look at the x direction. I always like starting with the x, just really for no reason at all. FAX minus the force of friction, which means we can jump ahead, and I'm going to take that and say that the applied force in the x direction minus the force of friction is going to equal mass times acceleration. Now, we need this force of friction, okay? In order to find the force of friction, we need Fn. So we need to go and look at our y component. I'll do it in purple over here. The sum of the forces in the y direction, that's going to be Fn minus Fay, plus Fay minus the force of gravity. All that's going to equal to 0 because this box isn't being lifted up, which means our normal force is now going to be this force of gravity mg minus our applied force in the y direction. So let's just go ahead and plug some numbers in here. We've got everything. So 10 times 9.81 minus our 19 applied force in the y direction. So what we have is a normal force of 98.1 minus 19, which is 79.1 newtons. Now I'm just going to highlight that just so we don't forget about it, because what we need now is to use this in our force of friction. So looking back at the x direction, our FAX minus our mu k Fn is going to equal the acceleration of the box. So this acceleration, if we just divide by the mass again, mu k times Fn all over our mass, well, we know everything here, right? We know what our FAX is, we know our coefficient of friction, we know our normal force, and we know our mass, which makes us super happy. So let's just plug and chug this. We've got our 40.8 x component, we've got our 0.3 coefficient of friction, we've got our 79.1 Newton normal force, and we've got our 10 kilogram mass, which gives us an acceleration of 1.71 meters per second squared. Now, if you notice, this is actually faster than part B, right? This is faster than pulling horizontal. Now, that's a really interesting result from this, which we will talk about a little bit during class, where we are actually pulling up on this box a little bit, so we are decreasing the amount of friction to a point where it's still an advantage. But if we pull too much vertically, we're going to lift this box up and we're not going to be able to go anywhere. So there is definitely a nice kind of boundary of how far, like what type of angle you can pull at to still be an advantage to you, which maybe we could calculate. Maybe I could give that to you on a quiz. I'm not really sure at this point, but that's a nice introduction to friction. Okay, try these next couple questions. We've got a second one Noah's pulling Sam across the sand in a toboggan, which is fun. And then we've got a person cutting their grass. So try these questions. We will go over them in class together, but hopefully this nice introduction to friction helped you out.